Hi, I'm Roz, and I work on wire-tailed mannequins. And um, in the past I've used video to study how birds fly and measured speeds and accelerations and turning performance of birds on video. And so I wanted to contribute to the video workshop at the Manakin RCN some things that I often think about in terms of the issues associated with measurement error. And so very briefly, I'm going to talk about what I mean by measurement error, why it matters, and what you can do. So often we have from video measures of an animal's position across multiple time points. And so often we want to use these video tracking data to obtain and compare measurements of the animal's speed and acceleration. So suppose we have 3 time points here indicated in blue. Velocity can be estimated as the change in the animal's position divided by the change in time. And we can do that for the time period between measurement number 1 and 2, and we can also estimate another velocity for the second change interval here. And so the slope of these kind of fuzzy lines that are drawn on top there would be the animal's velocity. Acceleration can be estimated as the change in velocity divided by the change in time, which would be the final velocity here, or the final slope here, minus the initial one divided by that change in time. But what I want to ask today is, what is the effect of measurement error on these estimates? And so I've indicated that by drawing these circles around these points, because in reality, our estimates of the animal's position aren't perfect. There's some fuzziness, some noise, some error around those estimates. And so I'm going to show you what influence measurement error has through this little simulation where I generated some fake data, and I did this using R. And I'm going to post this simulation on GitHub, and I'll add the link in the description of this video so that you can dig into the details yourself. So I'm going to just run the first part of the script, which generates some simulated data for an animal's movement over time, and then it plots the data. And so what we've got here on top is a plot of position in centimeters over time in video frames. So I'm assuming here that this is from 30 frame per second video, so this is 1 second and this is 2 seconds. And then I've taken these data and I've estimated the animal's velocity. And so you can see that this series has a really constant slope, which turns out to be a constant velocity of about 6 meters per second. And then I've used the velocity data to estimate the animal's acceleration, which is a constant value of 0 because the velocity is not changing. Now, what is the effect of measurement error on the estimates? In this first example, I've set an error value of 0, and that value gets specified in centimeters, and it gives me the standard deviation in centimeters of these position measurements. So let's see what happens when we make it 0.1. And so I'm going to rerun the data and regenerate the plots. And so this tiny amount of measurement error creates virtually no change, at least that I can see on this size of a plot. What if we make it 0.5? So now we've got a 5 centimeter measurement error. So now we can see that even though half of a centimeter is virtually nothing on the scale of this position plot, you can see how that noise is influencing our velocity measurements and our acceleration measurements. And I'll add that the gray lines here are the underlying true values. So this is what we should really be getting. And then the black dots are the values that we get after we what we would actually get from our measurements, our noisy measurements. Okay, let's try an error of 1 centimeter. So I hope what you're seeing here is how measurement error in the position data has an influence on our velocity measurements, but an even stronger influence on our acceleration measurements that are more derived and that rely on more position time points to estimate than velocity. And lastly, let's try a value of 3 centimeters there. And so you can see how noisy those accelerations are. Remember, they should be 0, but you can see how we can get wild changes in accelerations just by relatively small changes in position error. Okay, so in real life, the animal's velocity is almost never constant. When a golden collared manakin leaps from one sapling to another, it doesn't have a constant speed. It's accelerating as it leaves the sapling and then decelerates again as it lands on the next one. And so here I've simulated changing velocity and yet still a constant acceleration. But you can see how a very minuscule amount of measurement error in position still creates large fluctuations in our acceleration estimates. Now in real life, the other thing that happens is that we generally don't have the animal in the video frame for very long. We might be trying to estimate these quantities from only 5 or 6 or 10 frames. And if that's the case, it can be very hard to distinguish the animal's real accelerations from noise. So why does this matter? Well, in particular, if we want to do comparative studies, or if we even want to do comparisons among individuals within a species, we often are calibrating these videos for every display court. And in these systems, that means that each individual may have a different calibration. And to the extent that different calibrations can be biased or could be more or less subject to error, this means that some of our differences among individuals that we're measuring could just be differences in the calibrations or differences in the amount of noise. And that's something that we really want to avoid. We want our individual differences to capture something that's truly different about individuals, and we also want to be able to compare values across studies. So, what can we do? Well, here are some of the strategies that we can use to deal with this problem. The first thing we can do is to smooth the position data. And there's a number of different algorithms that you can use to do this. For example, you could use rolling averages, you could use a low S filter, you could use Kalman filters, or there are many other smoothing algorithms that you can implement in a lot of different programs like R or MATLAB. And I want to note here that commercial software that does tracking from video data, like the software that Leo demonstrated as part of this workshop, likely has a smoothing function built in. And so that's important to recognize. But the key thing here is that it's important to be consistent. So you should be wary about comparing values that were obtained using different smoothing methods or different video tracking methods in general. And as I showed you with that R demonstration, accelerations in particular are really sensitive to error, really sensitive to smoothing parameters, making it problematic to compare accelerations across studies that use different methods. Something else you can do is to ground truth your calibrations. For example, if you're measuring the size of a mannequin's leap, you might measure a ruler in each and every time you set up your video. You'd want to remeasure that ruler so that you have a ground truth for every video value. For accelerations or videos where you want to measure velocities, you can drop a high contrast object and measure its acceleration due to gravity. And you can do this repeatedly. And on average, the acceleration of your dropped objects should be 9.8 meters per second squared. And then I would recommend reporting these values plus or minus the range as an indication of your measurement error in your manuscripts. Now, I can't necessarily predict how changes to the setup, like how far away your camera is, I can't predict how that might affect the values you obtain, but what I can do is test that, be an experimenter about that, and compare the same ground truth measurements on 2 different setups. And lastly, another great way to deal with this is to take repeated independent measures of each individual, recalibrating your setup each time. So as I showed before on that map of the lens-tailed Manakin Lex, each male is going to be displaying likely at a different place. And so if you only took one measurement per male, then your calibration would be somewhat confounded with the differences among males. However, if you take repeated measurements of different males and recalibrate each time, that will reduce the chance that calibration error gets confounded with individual identities. And so that's all I have about tracking error. I'll post links between the videos and the R script online, and I hope that this was helpful.